Now, in the last video, we had calculated B part 2. That's the probability that Fred played cards given that he won a game. We saw that it was 9 over 13. Now, what does that mean? Well, we can say that 9/13 of all the games that Fred won were card games. So if we knew the total number of games that Fred won, maybe it's 100 games, then we get 9/13 of 100, and that would give us the number of those games that were card games. Of course, that means that the remainder, which is 4/13 of the games that Fred won, were racing games. Now we have to look at the probability that Fred wins a game, given that that game is cards. We don't have to go calculating this. We were actually given this in the question. We were given it here. It's equal to 0.3. You can see it on the tree diagram here. Now this means that 0.3 of the card games that Fred played were won by Fred. So you can see that these are two very different probabilities. And in general, they're not the same. You can see here, they're certainly not the same. 9 over 13 is not equal to 0.3. Now we have a new tree diagram here. We calculated the probability that Fred wins a game in B part 1. We saw that it was 0.26. It was actually 0.08 plus 0.18. Or if you like, out of 100 games, he wins 8 plus 18, 26 of them. So that's the probability that he wins. Well, there are only two options for Fred when it comes to the outcome of a game that he plays. Either he wins or he does not win. So we saw that in the question, because it says here, whichever he decides to do, he either wins or doesn't win, whether he plays, whether he goes horse racing or plays cards. So the probability that he loses or that he does not win is 1 minus 0.26. So we get 0.74. Now, in this box here, we're conditioning on the event that Fred has won a game, and we want to ask what is the probability that he goes racing given that he's won a game. So how do we calculate this probability here? So we're conditioning on the fact that Fred actually won a game. So we can use our conditional probability formula. This probability is the probability of R and W divided by the probability of W. So the event that's conditioned on appears in the denominator. So we can go and look up these probabilities from this tree diagram over here. We have 0.08 in the numerator. The probability that he won a game is 0.26. So that breaks down to 4 over 13. Now, what about this probability here? Well, in here we have to get the probability that Fred played cards given that he wins. So we're conditioning on the fact that Fred won a game. So once we know that Fred won a game, we know that that game that he won was either at the races or cards, one or the other. So these two probabilities must add up to 1. So we get 1 minus 4/13, which is 9/13. And we actually calculated this probability in part 2. Now, what is this probability here? Well, this is the probability that Fred wins and he wins at the races. So we expect this probability to be smaller than the probability that Fred wins, because the event that Fred wins at the races is more restrictive than the probability that Fred wins, because Fred could win at either the races or at playing cards. So we expect this number to be smaller. It's got by multiplying these two numbers together. So this is our conditional probability formula for the probability of R given W. We know it's probability R and W divided by the probability of W. So the event that's conditioned on is in the denominator. If we just cross multiply, we can get the probability of R and W, or the probability of W and R. I've written it the other way around here, but it doesn't matter. The event R and W is the same as the event W and R. And if we multiply these together, we get 0.08, as expected, because this probability should be the same as this one here. So we're talking about the event R, W and R, or R and W, same thing. So the probability associated with that event has to be the same. So if you multiply 0.26 by 4/13, you will actually get 0.08. So we can actually check that everything is consistent. Similarly here, if we multiply 0.26 by 9/13, we should get 0.32. Actually here, sorry, we should get this number here, the probability that he plays cards and wins. It's 0.18. We should get, yeah, I was looking at the wrong entry. The probability that he plays cards and wins is 0.18, and that is indeed what we get when we multiply 0.26 by 9/13. Of course, we could have done this part backwards. We could have started with these numbers, 0.08. We just get it from here. Probability R and W. This branch here, WR or RW, same thing, 0.08. And then take 0.08 and divide by 0.26 to get 4/13. Similarly here, we could have just looked this up from this tree diagram here. We see it's 0.18, fill it in here, and then take 0.18 and divide by 0.26 to get 9/13. So rather than using this conditional probability formula for these two branches here, I will fill in these two entries from this tree diagram. So the branch W prime R is this branch here. This is 0.32, so this must be 0.32. And then W prime C is 0.42. We know that if we multiply this number by this number, we get 0.32. Or in other words, the probability of R given W prime, which will go in here, is the probability of R and W prime, which is this here, divided by the probability of W prime. So 0.32 divided by 0.74. That's 16 over 37. Similarly here, this probability is 0.42. Get it from here. So we divide 0.42 by 0.74. So here we get 21 over 37. Of course, these two probabilities must add up to 1, because we're conditioning on the fact that Fred loses a game. So if Fred loses a game, well, there's two options. Either he lost at the races or he lost at cards. So these two probabilities must sum to 1, and they do. 16 plus 21 is 37. So we get 37 over 37, which is 1. Similarly up here, 4 over 13 plus 9 over 13 is 13 over 13, which is 1. Now in this question we want to see if events C and W are independent. Now if two events are independent, it means that if we get the probability of one event conditioned on the other event, then conditioning on the other event should not change or should not affect the probability. So in particular, the probability of C given W should equal the probability of C. And if this is true, it turns out that if we condition the other way, then the probability of W given C is actually the probability of W. So we only have to check one of these two. If one is true, the other is actually automatically true. So let's check to see if this one is true. If it's true, then the events C and W are independent. Well, it's only a matter of looking up these probabilities. The probability of C given W we saw was 9 over 13. The probability of C can be got from the tree diagram over here. We can see that it's 0.6. And 9/13 is not equal to 0.6. That means that C and W are not independent. Not independent means that they are dependent events. If they're not independent, then they're dependent. Now we want to consider events R and C. Are they independent? Well, if they're independent, then the probability of R given C should equal the probability of R. Or vice versa. We could say probability of C given R would have to equal the probability of C. Well, Actually, the probability of R given C is 0. The probability that Fred goes to the races, given that he plays cards, is 0 because we're given at the very start of the question that Fred either goes racing or plays cards. Okay, he doesn't do both. That's the situation here at the beginning of this tree diagram. Either he goes races, either he goes to the races with probability 0.4, or he plays cards with probability 0.6. So R and C are said to be mutually exclusive events. So if he goes racing, he doesn't play cards, and if he plays cards, he doesn't go to the races. So that's 0 probability. And what about the probability that he plays cards? Well, we know what that is. That's certainly not 0. That's 0.6. So you can see straight away that these are not equal. So that means that R and C are dependent events. Actually, I should have said here that the probability of R given C is not equal to the probability of R. Well, it doesn't matter because the probability of R is not 0. Probability of R is 0.4, which is not equal to 0. So that's the condition for R and C to be dependent. If these were equal, if probability R given C equals the probability of R, then the events are R and C are independent. Or if you like, you could look at this. The probability C given R would have to equal the probability of C if C and R are independent. And of course it's not true. This probability is 0. This probability is 0.6. So you only have to look at one of these